In this set of slides, we will talk about basic principles of modeling, with special emphasis on how they apply to combustion. Topics will include the definition of a state of a system and the difference between macroscopic and microscopic models, and these will be given with examples within combustion. An essential concept in modeling is the state of a system. This stems from the need to translate real-world objects into mathematical objects of a model. The essential concept of the state of a system is the description of the reality of the model. This is a set of quantities to describe our reality at any particular time and place, space, or whatever dimension we are modeling. The state represents the isolated set of quantities that we choose to watch within the model. The key to modeling is representing the real world in simple conceptual objects that a human can understand, or even data objects that a computer can understand. This involves translating real-world objects into mathematical quantities that eventually, through a program, represents the dynamics of the system. Since it is humanly and computationally impossible to include the infinite detail of reality, the goal of modeling entails isolating which aspects of the real world are relevant to what we want to describe. Which properties are included and how much detail within each property are included establishes the level or complexity of the model. The model acts on this space of states, producing the dynamics of the model. And within engineering systems, or modeling of the combustion process, it's often enough to describe the global quantities such as temperature and pressure. In detailed modeling, the relevant information is the set of reactions and thermodynamic properties of the information about the molecules. The model acts on another state to produce other states, and the process describes the real world. The state of a system is the heart of a model, and encompasses the objects within the model and the description of the objects. How the state is defined depends on what level of modeling and what the model needs. A more global model could involve a state with just the temperature, pressure, density, and other global quantities of the system. A more detailed state could be that of the individual molecule, for example, quantum mechanical description, which is a molecule describing the state of the electron clouds around a fixed nuclei. Or on a kinetic level, the state of the system can be the vector concentrations of the species, along with the global temperature and pressure. The kinetic model, described by the set of reactions between these species, gives the transformation of one vector state to another vector state after a given time interval. Within combustion, there are two common views of how to describe the combustion process, the macroscopic and the macroscopic view. Looking at the microscopic view, we see individual objects and their descriptions. For example, individual objects are each traveling at a certain speed. The reaction of molecules can be seen as these molecules colliding, resulting in the breaking and making of bonds, forming a different set of molecules. But since we are looking at an enormous number of these individual molecules, that we can look at a conglomerate of properties. This is the macroscopic view. Instead of the translational speed of individual molecules, we look at the distribution of speeds for a whole set of molecules. This, in turn, can be interpreted into a measurable macroscopic quantity like temperature. Individual molecules pounding against the side of a container, each at the different speeds, can, at a macroscopic level, be related to pressure. Combustion modeling makes use of both the microscopic view and the macroscopic view. Distinguishing between these views reflects the type of information one wants to extract from the modeling process. But the two views are not exclusive. They must coincide. Each individual view also helps in understanding the process involved, helps isolate the information that one is trying to extract from the modeling process. The macroscopic view consists of more global quantities. At an engineering level, for example in engines, turbines, combustors, and the like. Modeling is done at the macroscopic level because of the simplified modeling involved. One is more interested in the statistical or global quantities such as temperature and pressure changes, corresponding heat release of the process as a whole. An engineer is not so much interested in the exact reason for these changes. However, to understand more thoroughly the origins of the macroscopic quantities, one must look more at the microscopic level. Detailed kinetic studies examine the changes in the individual molecules. The origin of these changes is a consequence of bond making and breaking at the molecular level. The making and breaking of bonds can release or absorb bond energy. This in turn creates a global heat release, affecting the global temperature of the system. In addition, with bond making and breaking, the number of molecules changes and thus directly affecting the pressure. More importantly, now that the current emphasis is on reducing emissions, understanding kinetic system at a microscopic level is more important. The origin of pollutants, such as soot, NOx, can only be investigated at the microscopic level, identifying the individual source molecules involved. If one understands the source of pollutants, then one can investigate under which conditions less pollutants are formed, especially explaining more thoroughly the observations that certain pollutants are reduced under certain conditions can aid in optimizing the process and to reduce the emissions even more. The bottom line is that understanding a process is not just an academic exercise. It has an important consequence in the real world of engineering. The ideal gas law is an equation representing the relationship between essential macroscopic states of a gaseous system with temperature, pressure, volume, and the amount of a substance. The ideal gas law models molecules as non-interacting objects with only translational energy colliding with each other with no molecular interactions like billiard balls. The assumption is good for high pressure and low densities. In most combustion kinetic models, the ideal gas law is assumed to hold. The ideal gas law reflects the proportional dependencies between the macroscopic quantities of temperature, pressure, volume, and the number, or moles, of particles. The ideal gas law describes a system in a volume of n moles of non-interacting molecular balls, like billiard balls, zooming around with a given average translational energy, represented as the temperature, hitting the wall producing a pressure P. The Rydberg constant, R, gives the proportional relationship. If the gas molecules do not act like non-interacting billiard balls, then it does not have ideal gas behavior. Non-ideal gas behavior occurs when the molecules start interacting with each other. The molecule is not a hard sphere anymore. There is an interaction caused by electron attractions and repulsions. For example, with van der Waals forces or electrostatic forces. This can happen, for example, in solids, liquids, and plasmas, or under high pressure or high density conditions, which is the opposite of the ideal gas conditions.